Okay. So, good evening, everyone. So, this is the ninth problem solving session for the course Nanomaterial and Their Properties. I'm Sept. Yeah, we have 3 more sessions left after this. Yeah, I think in last class we talked about how where Hall patch equation fails. You have Hall patch equation and inverse Hall patch effect. Um, okay, so up till this point, okay, till this point. So the grain size versus a hardness scale, to take log, we'll get half. This half a slope comes from log sigma there. So log d to the power minus half. So if you can take this out, minus half log d. So the slope of this log plot will be 0.5. So in the Hall patch strengthening, what's happening is if you have a large grain at the grain boundaries, dislocations will pile up. Okay? New dislocation is generated and they'll start piling up at the grain boundary. Okay, so here you can see a lot more dislocations are there. As you go down to smaller grain, this dislocation spacing doesn't depend on the grain size. It depends on the back pressure applied by each dislocation. This more or less remains same. So now you have lesser number of dislocations that can come in. After this point, when uh, suppose if you go even smaller, only few dislocations will exist. So now causing additional plastic deformation will not be possible since you have generated a lot of dislocation. Now the dislocation have to move from one grain to another, and that requires much more energy than to just create dislocation. So as you're reducing particle size, you're piling up more and more dislocations. So that's the reason you get this deadening. However, after a certain point, if you go even smaller, now only one single dislocation can exist. Now you cannot generate another dislocation. So at this point, now there is uh, nothing here. The dislocation piling up. This was applying some back pressure on the dislocation generated. That was preventing dislocation formation. However, since there is no piling up here, there is no back pressure, and now the dislocations can easily form and you get plastic deformation again. So after this point, your Hall patch relationship starts to break down after around 10 nanometers. And yeah, so this is called inverse Hall patch effect. Where the particle size is so small that only a single dislocation can exist. Thermal conductivity. So there are two main mechanisms for thermal conductivity in materials. First is electron, and second is phonon. So what can happen if we have hot and cold side? What will happen is from hot side, these electrons will have higher energy since it's hotter, so they'll have more energy. They will diffuse to cold end, giving their energy to the electrons present here. So this is just transportation of heat through electrons. Another way is through phonon. Now these, if this side is hot, both electrons and as well as the atoms which form the lattice, they also vibrate more. Their vibration, so if this one vibrates like this way, there will be repulsion on this one and this one also vibrate. So there will be a collective oscillation of these uh, phonons. So I think there are two modes, optical and acoustic phonons. It just depends how the vibration is happening. So if the vibration was like this will also vibrate. will also vibrate. And so this there will be kind of wave generated which will move forward. So with this wave, vibration wave, you're carrying thermal energy with it from hot to cold side. Okay. So as you go down to uh, nanometer scale, nanoparticles, what happens is um, these phonon waves themselves do not have much space to travel, so the thermal conductivity changes. This is band structure. If you have 3D material, your bands look something like this. So this is the energy, this is A, the wave vector along these wave vectors. All energy levels are possible. There's a continuous distribution of energy. Okay. However, if you go down to 2D, what will happen is there will be gaps now. We'll still follow the parabolic path, but now there are gaps, gaps now. It's 3D, 2D, and 1D. Yeah, is something similar. Yeah, just imagine it horizontally. So here you can have all possible energy levels. Here now you have discrete energy levels, and this still follows this parabolic path. In 1D, you have even more discrete. So here still you have can have these energy levels. There are some continuous zones. As you go down to nanowire, again, like these energy levels, they're changing. Will still follow this parabolic path, and at 0D, then you have this discrete side. So your electrons cannot have any energy they want. They will only have these particular energy states to occupy. Okay. Now, we'll start with the practice questions. For nanomaterials with grain size less than 10 to 15 nanometer, which of the following is true? So for particles less than 10 nanometers, you saw, yes. For less than 10 nanometers, fall in this region. This region was, uh, there is, you cannot form more dislocation since uh, the dislocation spacing is less than the particle diameter. So your d particle diameter is less than the d. If your ratio between these two is less than this, so if it's less than that, what will happen is primary dislocation source. These are the sites where dislocations are formed. So in case of larger particles, as you apply strain, the dislocation starts from this point and it moves. Okay, it moves to this point. So the point where dislocation is generated is your source of a dislocation. So if your particle size is too small, these dislocation sources cannot form. So different sources for dislocation generation is impossible. If the particle is very large, this dislocation source will be easier. Ungrained diameter is greater than the Berger vector. These are the Berger vectors. Grain diameter will be less than the Berger vector for nanomaterial. For inverse Hall pitch relationship, which is for true for inverse Hall pitch equation relation. After a certain point, even it starts to decrease. Obviously, start to decrease. Your hardness starts to decrease with decreasing the grain size below this 10 nanometer. If the Hall pitch relationship was true, as you decrease particle size, the strength should increase, so hardness should increase. And that is only up till 10 nanometers, greater than 10 nanometers. Uh, greater than 10 nanometers. Okay. Less than 10 nanometers, the inverse happens. As you decrease D, your sigma decreases, so your hardness is decreasing. It's rectangle. So melting temperature of embedded nanoparticles should have higher than bulk melting temperature when the interface energy gamma between solid, liquid, and matrix. How does that vary? Okay. So the formula cos theta is gamma ln gamma sm. Well, so for melting point to be higher than bulk, this cos theta should be greater than 1. For cos theta to be, if this value is greater than 1, then gamma lm minus gamma sm should be greater than 1. Where gamma lm should be greater than gamma sm. There we have formula correct. So how do you define contact angle? If this is a drop, this is a drop. This is your gamma ls, gamma s and matrix. So the contact angle you define is between the liquid and the gas interface and this your liquid solid interface. This is your theta. If your theta is close to 0, what case will be close to 0? It's perfectly wetting. Just assume like very large. It's like almost wetting. What will happen is your theta will be is going close to 0, right? So if theta is 0, you have hydrophilic surface. Yeah, so this is perfectly wetting. Okay. And the other extreme, if the drop is just sitting on the surface at just one point, theta becomes 180 degrees. Okay. And any angle above 120, I don't think in practical you can get 180 degrees, but angles 120 degrees. Greater than 120 degrees. These are your super hydrophobic. Phobic surface. If it's a 90 degree, the droplet would look something like this. Okay. Anything over 120, we classify them as super hydrophobic. So theta is greater than 120 degree. Thermal conductivity in diode. So we just saw you can have thermal conductivity either due to electrons or through phonons. Diamond, we know, is an insulator. So it doesn't conduct electron. So only through free electron is correct. Both through free electron and incorrect. Only through lattice. But the structure of diamond allows it to have very good lattice thermal conductivity through phonons. So diamond is really good conductor. And in some like PC cooling gels, they have diamond particles inside it. So diamond is an insulator, so there's no risk of shorting your chip components, and it has very high thermal conductivity. It gives your gel good heat transfer capability. So suppose you have your CPU and the CPU, and you add a metal block on top, this will be copper. At the interface, you want a good thermal conductivity, right? Like no mechanical, if you use mechanical screws, there will be small air gap left between them. So you want to cover up that air gap, so you use thermal gels, thermal paste to fill that void. So some of these thermal gels contain diamond. So it's insulating and very high thermal conductivity. Which of the statement, which one is the wrong statement? Specific heat of machine. Okay, specific heat of a material. So specific heat is defined as energy required to increase temperature by 1 degree Celsius per kg of material. So this unit will be joules, energy required per unit Celsius per Kelvin into kg. Okay, joules, this is correct. We have to find the wrong statement. Heat capacity per unit mass. Heat capacity is again energy required to raise temperature by 1 degree Celsius. That has unit joules per Kelvin per unit mass. So that's again equal to specific heat. Constant for a material, yeah, it's a material property, remains constant. It is our intrinsic property. So whether you have one kg of water or 2 kgs of water, the specific heat remains the same. Think for ice around 840. I don't remember. 840 was maybe it's say 840 per Kelvin kg. So that remains same whether you have 1 kg or 2 kg. So it doesn't depend on the amount of material. So weight, for example, is an extrinsic property. What else is extrinsic? Length, volume. Okay, these are all extrinsic properties. Intrinsic are like specific heat, density. These are so this is incorrect. So that's why only C is correct. What is the energy at a given level and for all n is equals to nx and y and z is equals to 1 for free electron in solid cube with dimension 10 cross 10 cross 10 mm. Okay. So for solid cube, three dimension material, E is equals to pi square h square 2 ml square into nx square plus ny square plus nz square. Okay, this is h bar square. Okay. Here h bar is 1.05 into 10 to power minus 34. Your m is the electron mass 9.1 to 10 to power minus 31. L is given 10 nanometer or 10 millimeters. L is equals to 10 into 10 to power minus 3 meters. 10 to power minus 2 meters. And your n square and y and z and equals to 1. So energy is equals to pi square times 1.05 into 1 minus 34 whole square divided by 2 times 9.1 into 10 to power minus 31 into 10 to power minus 2 square. Okay, so just plug in these values and you should get let's pi square into 1.05 square divided by 2 into 9.1 into 10 to power minus 68 plus 31 plus 4 pi into 1.05 square divided by 2 into 9.1 into 35. So 3 minus 33. Only something into 10 to power minus 33. Okay, all of them minus 33. So you have to calculate them. So you'll get around 1.8 into 10 to power minus 33 joules. Okay, so you should be the correct answer. Based on Fermi-Dirac statistics, at temperature more than 0 Kelvin, the probability of occupation of at Fermi level EF is. So your conduction band, so yeah, this is your conduction band, valence band, somewhere in between. So for silicon at 0 degree Celsius, 0 degree Kelvin, the Fermi level rise in the middle. Yeah. So Fermi level, what it means is where occupation probability is zero point 0.5 or 50%. So you have 50% chances of finding an electron at this level, energy level. So it's yeah. Okay. This is wrong. This is not valence band. This is opposite. This is a conduction band, and this is your valence band. Once electron jumps from valence band to the conduction band, it is free to move around. At 0 degree, 0 K, probability of finding electron is unity 1. So again, this is your valence conduction band, your valence band. Valence band is completely filled with electrons at 0 K, and your Fermi level lies here. So at E is equals to EF, your probability is zero point 0.5. As you go down to the valence band, here your probability becomes 1. So for energy less than EF, it's limited. Forbidden energy band gap of semiconductor material measured in EK's diagram is the difference between the EK diagram. I can pull up silicon structure. This is a band diagram for silicon. This is your energy versus K. This is your forbidden energy gap. Okay, so now for conduction, this is your valence band. So this point is your global maximum of conduction valence band, and this point is your global minima for conduction band. The difference between global maxima for valence band and global minima for conduction band is your band gap. Mhm. So global minima for conduction band and global maxima for valence band. Okay. Right. Hardness of a material is a measure of hardness is a measure of a strength of a material. Strong it will to quantify that. As a dislocation can only move. So this is your as a dislocation. So it can only move along this slip plane. So move only on the slip plane. Last time there was a question regarding Berger's vector, how the Berger vector is located for edge and the screw dislocation. So suppose this is your Berger vector, so your edge dislocation. This is your edge dislocation. This one. Okay. What you do? Suppose you start from here, you complete a loop. Okay. So suppose I start from here. I go three up, or maybe four up. One, two, three. Okay, three up, three to the side. One, two, three. Three back down. One, two, three. And go back. One, two, three. And I started from here, and this is my end point. Start and end. The difference between these 2 points is your Berger vector, whatever B. And your edge dislocation is inside this plane, inside or outside this plane. In this case, it was inside the plane. So your Berger vector and your edge dislocation are perpendicular to each other. So B is perpendicular to edge dislocation. Okay. However, if you do this in screw dislocation, I suppose you start from here. Okay, you go up one, two, three. Go to right one, two, three. One, two, three. You go. Okay, let's start from here. One, two, three. Three left. Three up. One, two, three. Three right. One, two, three. Now if you go down, three down. One. You will be inside the material two and three. So there's a gap between the. So this was on the surface and this is inside this material. There's a difference of one Berger vector inside. So the Berger vector is this way, and your screw dislocation is also this way. So these two are parallel to each other. So in screw dislocation, Berger vector is parallel to screw dislocation. Okay. The motion of a dislocation in polycrystalline nanomaterial is dictated by. Okay. So motion of dislocation in polycrystalline nanomaterial is dictated by. So back stress, true, as dislocations pile up, these dislocations experience a back stress. So motion is affected by this back stress. This grain boundary is stopping these dislocations to move forward. It's also affecting it. And of course, slip plane is affecting motion because the dislocation move along these slip planes. So some slip planes have higher or lower energy than you can. So dislocations can move easily. Some have higher energy. All of these are correct. In nanocrystalline material, hardness increases with. So in general, Hall patch effect plays a role. So sigma is proportional to d to the power minus half. The grain size decreases, d decreases, yes, sigma increases. So b is correct. Why the Hall patch equation breaks down beyond a certain grain size? You remember, your grain is very large, the dislocations are able to pile up. Okay, and then move. However, if your grain is very small, only a single dislocation exists. So it is not possible for piling up of dislocation since the grain is very small. Right answer. Piling of dislocations considerable number leads to this breakdown. Now, pile up is what gives the whole pitch equation, is the reason for the whole pitch equation. Increasing grain size leads to increase in elastic modulus. We say effects like dislocations exist only in disordered state of material. Disordered state is amorphous. False. Dislocations mostly exist in crystalline materials. So if you see this image, this is a perfect crystal, right? Only there's a dislocation here. Other than that, this is a perfect crystal. And grain size of ordered structure is gradually reducing, and below a certain critical value of grain size, the material turns to an amorphous. However, the yield strength of the material in the amorphous state in the amorphous state rises to very high value and gigapascal as compared to yield strength of nanowire or even much higher. So as you go down to very small levels in amorphous material, uh, there are no dislocations. What this causes is there are no dislocation, there is no dislocation movement. So there is no plastic deformation. This is what happens in glasses. Glasses have very high yield strength. So if there is no plastic deformation, your stress strain curve looks linear almost. Okay, stress and slope is there. And this is the yield strength. Sigma is Young's modulus phi. Okay, so this is true. As you reach the amorphous regime, since there are no dislocation movement, because there is no dislocation, you get very high yield strength. For a particular system, the melting temperature of the nanoparticle varies as a function of, so if you remember the formula, T melting for nano is Tm for bulk, 1 minus gamma SL divided by LR. Melting particle variable. So it depends on the particle size R. Then is the latent heat, is there interfacial energy, yeah, so then the particle size. Melting melting temperature Tm nano of the emitted nanoparticle will be less than the melting temperature of bulk. So for this condition to happen, your cos theta, which is gamma ln is gamma sm divided by gamma sl. Theta should be greater than 90 degrees. The cos theta will be less than 1 or less negative. Okay. So this will be less than 0. So gamma Lm minus gamma Sm less than 0. So gamma Sm gamma Lm will be less than gamma Sm. B option. Correct. Check the free energy versus temperature curve. Below the melting temperature. So if you have your phase diagram, okay, this is liquid, liquid plus alpha, alpha. This is a solid. So below your melting temperature, this is your melting temperature. Below this is your alpha, which is solid phase. In insulator, thermoconductivity conduction is defined by so as you saw, like in case of diamond, thermal conductivity is majorly done by photons. Since its insulator, electrons are not available to freely move, so they will not transport any thermal energy too. How band gap of crystalline material is defined? Uh, this is your conduction band. This is your valence band. The energy gap between these two. The bottom of your conduction band and top of your valence band is your band gap. Okay. Quantum confinement is found in nanomaterials. Bulk there is. This only comes into play when your size, any dimension is less than 10 or 50 nanometers. 10 to 50 nanometers. In 2D nanomaterials, quantum confinement happens. First, it's a 2D. Where only this thickness T is less than 100 nanometers. So only along this direction the quantum confinement will happen. So only in one direction. Even this P should be like less than 10 nanometers, 5 to 10 nanometers. not in 50, 5 to 10 nanometers. Suppose you have two microstructures of the same metal. In one micrograph, the average grain size is 20 nanometer. The other is in 1 nanometer. So as you know, hence, how will the strength of material will vary in the latter case? So this is D is greater than 10 nanometers, so it follows the Hall-Petch equation. The sigma is sigma naught plus K D to the power half. As your D decreases, your sigma should increase, your strength should increase. So for the latter case, which is this, particle size is larger, so your strength will be less. Yes. Okay, so I can begin this week's assignment. Last week's assignment. Phase transformation, temperature varies. So your equation delta T uh, delta T transformation alpha gamma T bulk rate of transition transformation into D theta. So your particle size D is inverse, and your surface density gamma direct. Uh, C is correct. Yes. Inert gas condensation method applies to production. Inert gas condensation method of nanoparticle production applies sequential growth scheme. Yeah, so remember the code figure. And these are mechanical scrapers as the nanoparticles are growing. So, and what happens in this? There's growth happens in steps. So you get this core shell kind of structure. That's why it's a sequential growth scheme. What is the role of soul in soul gel method of synthesis of nanoparticles? Uh, Remember this slide? So you have your discrete nanoparticles. This is your soul. It prevents these particles to come in contact with each other, and thus restrict the growth of these nanoparticles to bigger clusters. It's just preventing them to like touch each other. If they're able to come in contact with each other, the children may start taking place and they might start growing and they'll grow to a larger particle. Okay. Synthesis of a material, of a nanomaterial from bulk is called. Remember slide. If you go from bulk to smaller sizes, macro to like nano, go down. So this is called the top-down method. Each of these is a common PVD method, physical vapor method. Reactive ion etching. This is etching is a different method. I don't think they mentioned it here, but this is etching is a different process. Sputtering, you can see, is a PVD method, pulse vapor deposition or physical vapor deposition. So sputtering, modified chemical vapor deposition. So these are all CVD methods. CVD chemical methods. So plasma activated chemical CVD and modified CVD. So sputtering is a common PVD method. What are the major advantage of CVD over PVD? So usually to have reactions to take place in CVD, you have higher temperature. In CVD, since you are starting with gas molecules, they take some time for the reactions to take place. So this is also slower and typically it is more expensive. because you need to have all the arrangement for storing the gases and all, and the vacuum chamber where the reactions will take place. So generally, it's more expensive, but it gives you better quality of film. So it has better coverage. So what will happen? Suppose you have your step in PVD. What will happen is small chunks will come and they'll sit over these places. Okay, they'll mostly all come parallel to each other. Okay, however, this step is uncovered. There's no deposition happening here. Whereas in CVD, your gas molecules are present everywhere. Okay, they'll uniformly form nanoparticles all over the surface because gas is present everywhere and reaction will take place everywhere on the surface. It has better step coverage, CVD. Yes. High volume fraction of grain boundaries in nanocrystalline material results in high volume fraction of grain boundaries in nanocrystalline material results in. So if you have large fraction of grain boundaries, you'll have a lot of energy trapped in these grain boundaries. So as you know, grain boundaries are high energy sites. Grain boundaries are high energy sites because of incomplete bonds. So as you have more large number of these grain boundaries, you'll have high grain boundary energy. Since all these grain atoms sitting in the grain have unsatisfied bonds, so they have more tendency to react. So they're also uh, less stable thermally. Okay. So this also happens as you increase the temperature. These um, grains would want to grow into larger particles, thus reducing the grain boundaries. So if these smaller particles grow up, larger particles, so overall their number of grains are length of grain boundary is decreasing. Okay. There, if you measure all the length of all these grains, now you only have this much grain boundary left. They'll agglomerate. Suppose you have two microstructures of same metal. Oh, this we already did. But yeah, again, sigma is equals to sigma naught plus k to the power kd to the power minus half. So microstructure, one micrograph has 20 nanometer, other has 1 micron. 1 micron or 1000 nanometer. Okay. So this is your D1, your D2. Since D1 is less than D2, sigma 1 will be greater than sigma 2. Your strength will be larger for 1, 2. So strength will be less for 2. Okay. Self-interstitial defects. Self-interstitial defects. So suppose you have a body centered in itself, and then there's one sitting at the center. So self-interstitial is one of these. This atom may be missing and sitting somewhere in this void, maybe over here. So this is a void. Okay. So this moves to the side. This is missing. What is it? This atom has moved from here to here. Right. This is self-interstitial defect, where one of the atom moves to a interstitial site from the lattice point. And this is mostly common metals because all of them have same size and it's easier for them to go into interstitial sites. Okay. Three important things essentially control sintering in spark plasma sintering process. So in SPS, SPS, filtering. You have your powder inside a mold. There's a die involved, and there are two die pressing force, and you pass lot of current through it. I this current will have your I square R heating this. So if you want to heat this powder to almost like the melting temperature, you need very high currents. Current can be like 1000 or 2000 amps. Okay. With low voltage, usually like power is current times voltage, right? I times V. We just want very large current. We can have low voltage to have the same power. And usually these nanoparticles inside have upside layer on the top. There is this thin oxide layer on top of these all these particles. But uh, between these two nanoparticles, there will be sparking taking place. That spark breaks down these oxide layers. The spark breaks the oxide layer, which reduces resistance and will cause some more undulating. This will also reduce the resistance, and also once these oxide layer is removed, these particles can come into contact with each other and diffusion can start taking place, thus allowing sintering to take place. Okay. So we want very high current breakage of this oxide layer between neighboring particle through sparking, and finally atomic migration, which is the diffusion. Okay. Diffusion, which is basically the sintering process. Okay. Yeah, this was the last question from the assignment. Do you guys have any questions about this question, these assignment problems? No. Um, okay, anyways, if you guys don't have any questions, I'll upload these slides on Google Drive, and the recording will be shared on YouTube on our 27. And yeah, be sure to submit the next assignment. This due this Wednesday. Okay, have a look at this. Right. Primarily mechanical property of material is determined by the stress strain curve. Flow curve, if you remember, is your plastic region and log plot where your strain hardening is taking place. Wherever strain hardening is taking place, you are in a plastic deformation zone. Okay. It tells crystalline material dislocates. Dislocation is characterized by so if the Berger vector lies in plane or perpendicular, then you can say it's either a screw or edge dislocation. State whether the statement below is true or false. If main boundary material does not allow dislocation to move forward, the grain material becomes strengthened enough. It should be generally true. Hall patch equation we've seen multiple times. Sigma and your grain size. According to Hall patch equation, what happens to the yield strength? Again, Hall patch equation, arithmetical representation of Hall patch equation 5, 6, 7, the same question. So same question. For which range of grain size does the Hall patch relation begin to fail? Inverse Hall patch effect. As we saw, very fine grains, less than like 10 nanometer, is where it typically starts to break down. But to seriously say it, strength starts to decrease in like 5 nanometers. Why the Hall pitch equation breaks down after a certain grain size? There's no piling up happening. Plasticity in material arises from uh, plasticity is just plastic deformation happens due to dislocation movement, dislocation generation and movement. In 2D nanomaterial quantum point confinement effects happen in this we already covered in the class. Yeah. Okay. So be sure to submit the assignment before Wednesday. Okay. Thank you for joining. Good night.